Welcome to this M1 video on displacement time graphs. Now, next few videos we're going to be basically looking at constant acceleration and things to do with that, and the first kind of few videos is just based on the graphs. So displacement time, velocity time and acceleration time. So just to look at the graphs, so there'll be a few short videos before then we get into the constant acceleration formulae. Now, with a displacement time graph, we're going to plot displacement on our y-axis and time on our x-axis. And there's effectively a couple of different ways in which you're going to see graphs. So if I have a graph, for example, that is, and I'll draw this in a black line, a straight line, a horizontal straight line. That means that at this point, you look at the displacement isn't changing, but time is changing. Time's increasing, displacement isn't increasing or decreasing. Okay, so that means there's no change in the displacement, so the object is stationary. Okay, now if I have a straight line but an increase in straight line like this, that means that as time increases, displacement increases, but it increases at a constant rate. Okay, so that means that it's going or moving at a constant velocity, and the gradient of this line will give me the actual velocity. Okay, because its velocity is the rate of change of displacement. And finally, if I have one that's kind of like an exponential, getting steeper and steeper, then that is the velocity is increasing. Because as time goes on, the displacement increases quicker and quicker and quicker. So that means the object is accelerating. Okay, and that's basically the main types of graphs. Obviously we could have, instead of going up like that, we could have it going up quicker and slowing down. Okay, to be decelerating then. Okay, because the gradient, in this case, the gradient is increasing. And if I drew it like this, the gradient would be decreasing. Okay, so that's kind of like, you know, a little bit of interpretation of what the kind of graphs that you would expect to see would look like. Now let's just talk about the difference between velocity and speed. So average velocity and average speed. Okay, because they're two different things. Yeah, velocity also has direction, whereas speed doesn't. Okay, so that's one important thing to remember with velocity. Now, average velocity is the displacement over time. Now, displacement from your starting point. So if you went from a start, let's draw a quick graph. Okay, so if I had a starting point here, just at the origin, and I drew it up like this, and then I drew it down like this, and I wanted to measure the average velocity, then what I would actually do is the displacement, which is this distance, okay, this distance here, the displacement over the time taken, which is that. Now speed is a little bit different because that is the distance over the time taken. So that's the total distance. Okay, so if I had a similar graph here, but this now would be, say D for distance. Okay, could still be displacement. Okay, I'd have to measure to this point and then measure to this point, because I'd need the distance to get there plus this distance, and that would give me the total distance divided by the time. So in this case, the speed and the average speed and the average velocity are different. They're different values. Okay, now a lot of the time we do kind of interchange the word speed and the word velocity, but it is important to kind of understand the difference between them. Now let's look at an example. So here we have a displacement time graph, and it shows the journey of Tom on his route to his friend's house one morning. So here's the journey, and we've got to work out the average velocity for each stage in Tom's journey. So A, B, C, and D. Okay, so average velocity for A is going to be the distance 100 meters over the time, which is 2 minutes. Now, meters per minute isn't really a velocity that we use. Meters per second, kilometers per hour, those would be, velocities and in turn speeds that we would use. So that per minute I'm going to change into seconds. So 100 meters and 120 seconds. And that gives me 0.83 meters per second. Now, the average velocity for B, well, that'll be 0 over 1 to 3 minutes. So over 180, but that's 0 meters per second. We know he's not going anywhere. C, now that is going from 100 to 300. So that's going to be a displacement of 200. And then in terms of time, it's taken in 1, 2, 3, 4 minutes. So that's going to be 240. Now that should be the same as A. Yeah, so 200 divided by 240, 0.83. But it has the same gradient, therefore I was expecting the same average velocity. And then for D, we've got from here down, so 300. And then in terms of time, we've got 1, 2, 3 minutes. So that's going to be divided by 180. So 300 over 180 is 1.67 meters per second. Okay, so that now is the average velocity from each stage of the journey. Let's look at part B. State the average velocity for the whole journey. So you can see here, he started here and he ended up here. So his displacement is 0. So with a displacement of 0, his velocity will also be 0. So we can just state that. Now work out the average speed. So the average speed will be his total distance. So he travelled all the way up 300 meters and then 300 meters back. So in total, he went 600 meters. And that took him 12 minutes or 720 seconds. And 600 divided by 720 is, oh, lo and behold, 0.83 meters per second. So that was his average speed. Okay, so hopefully you can see just the difference between the velocity and the speed and just simply how to work them out. It is just the gradient of the straight line. Okay, so this gradient, so just like you could, if you had the equation of the line, you could differentiate, couldn't you? And use that to find the gradient. Okay, but anyway, that is all we've got for this example. It's nice and straightforward. I'll give you 1 or 2 questions just to have a go at, and then we'll move on, finish the video, and hopefully you guys will jump into the next video. Before we look at the questions, I'd like to just remind you now to subscribe if you are not a subscriber, so that you can easily find my channel if you want to watch more videos from the International A-Level course. And if you are a long time subscriber and you want to give a little bit back, then consider hitting that join button and join for 1 month, 2 months, whatever you're able to. It really helps me continue to make these videos. Anyway, let's look at the questions. So 2 straightforward questions, and it is straightforward at the beginning of M1. Okay, so 2 straightforward questions. Pause the video, have a go at them, and then hit play to check out the answers afterwards. Okay, first part, work out the velocity in part A. So this is quite straightforward. Okay, the distance or the displacement is 10 kilometers. The time is 1 hour. So 10 kilometers per hour. Nice and easy. Now, on her return journey, Lucy carried on past her home for 5 kilometers. If she left home at 9 a.m, what time did she pass her home? So it's this point here. Now we can see that this is 2.5 hours. So that would be 9 plus 2.5, so 9, 10, 11, 11:30 a.m. If it wasn't so obvious, this passing point, what I would do is, because this is a straight line, I'd work out this velocity. So I could pick 2 points that I know. So we're starting at 10 kilometers here, and then this is 5 kilometers, and this distance here is half an hour. So I could see what the velocity that she's traveling here, which is 10 kilometers an hour. It's the same gradient as this one, just the negative gradient. And then I could work it out then, you know, from here to here, how long, and then add that time in. So I can work it out by working out the velocity first if I needed to. Right, part C. Calculated Lucy's average speed for the whole journey. So her speed is going to be the total distance. So that's 10 plus 10 plus 5, so plus 15. So that's 10 plus 15 plus another 5 here back to her home. Okay, and that is over 5 hours in total. So that is 30 over 5, which is 6 kilometers per hour. And that's all there is to it. Nice and easy. Let's look at question 2. Okay, so part A. What is the velocity of the ball at its maximum height? So at its maximum height, the velocity is 0 meters per second. Because we're going up and we're slowing down until we hit 0, and then we are accelerating in the opposite direction. Now, describe the motion of the ball from when it is thrown to when it hits the ground. So the velocity of the ball is positive. If we do that first, which is the upwards direction, okay, and decreases until 0 and that's at its max point. And then after that, then the velocity is negative. Because velocity has direction. Okay, so the positive and the negative signs just mean opposite directions. And its velocity increases until it hits the ground at the same speed which it was launched. Now notice I say in the same speed. It's got to be the same speed and not the same velocity, because velocity has direction. So it wouldn't be the same numerical value, but one would be positive here and negative here. Okay, obviously this doesn't take into account any air resistance, but if it did, it should still work out the same, because the air resistance would be slowing the ball on the way up, and the air resistance would then kind of limit the acceleration of the ball on the way down in the same way as it slowed the ball. And not necessarily, gravity obviously slowed the ball completely, but you know, air resistance played a minor part in it. Okay, but that's all there is to this video. Okay, stay tuned for the next one on velocity time graphs.